Okay, so I think it's time to start already. My name is Dmytro. I'm here today to talk about build tools we commonly use at Grammarly, namely GitLab, Gradle, and Docker. Not every team uses Gradle and Docker, but pretty much every team uses GitLab, I believe. And I'm going to talk about build optimization mechanisms and how to make your builds more efficient with these tools. Short disclaimers. This is my first public talk in a really, really long time. So forgive me if I'm a little bit nervous. Although I see less people than I expected, so probably it's going to be fine. And the second disclaimer is I'm not a long-time expert on those tools. Everything I learned in my short tenure at Grammarly, which is 4 months, I believe. So when I just joined Grammarly, I quickly onboarded on a completely new project, single sign-on, which was built from a clean slate. And one of my first tasks was to create a skeleton for that project, which included some build process for it. And I made a really deep dive into that task. Later, gave me some information and gave me some source to make this talk. So let's start with defining build goals that we want to achieve with build process. I defined 3 build goals. Main of them is probably reproducibility, because this means correctness for build process. If with the same set of inputs, you cannot reproduce the same build output, then it means your build process is completely incorrect. Second is probably speed, and the least important is simplicity, because it's kind of subjective. It depends on the depth of your personal knowledge of build tools you use. And the speed goal, you can actually split in 2 separate goals. One is isolated build speed or clean build speed. And the second is incremental build speed, meaning the speed of subsequent builds. If you have compiled 200 classes in your first build, you downloaded all the third-party dependencies in your first build, then if you change one class in your second commit, maybe you don't need to do all the work from scratch on your second build. Maybe you can save some time and make an incremental build much faster than the first one. Now, with this set of goals, when you look at goals, you should always ask a question, is there a conflict? And yes, there is a conflict in these goals. The biggest conflict is between incrementality and reproducibility, because reproducibility is usually achieved by running your build in a disposable environment and not passing any artifacts and any files between environments for 2 subsequent builds, essentially. So every build is a clean build. And this was the goal when continuous integration tools were first introduced, I believe, to have a disposable environment for each build. So each build is easily reproducible, and you never have weird side effects of builds. But incrementality actually requires you to pass some files that will help you to make subsequent build faster, namely cache files. And so these goals are in some sort of a conflict. And the way to resolve this conflict that I can propose is to prefer reproducibility for master branch and do clean builds every time you build master branch, and to prefer incrementality in other branches. So when you work on some features, you can get subsequent builds fast enough and see results of your changes very fast. Now, there's also some conflict between simplicity and incrementality, but the way to resolve it is you just should look at the size of benefits of incrementality. Like if you implement some optimization and it saves you 5 seconds, maybe it's not worth making your build much more complex and complicated and harder to understand for other developers on your team. So you should weigh in the benefits of incremental speed. Now, my talk is about 3 build tools. So first build tool I'm going to cover is Gitlab. Let's cover what Gitlab has to offer, and then maybe we'll see how to use those offerings by other tools like Gradle and Docker. So Gitlab has 3 optimization features, and this might surprise you a little bit because artifacts is a feature that is usually not thought of as an optimization feature, but in Gitlab particularly, it's used not only to present the final results of your build, but also to pass intermediate results on different build stages from stage to stage. And this makes artifacts a viable optimization feature that allows you to avoid double work on different stages of your build. And persistent volume is something very similar to cache. Basically, it is a local cache, and I'll cover it a little bit later. So small concept recap for those who never learned GitLab concepts or maybe forgot them. I think this is quite a useful diagram I made on this weekend. And basically, it explains the concepts of pipelines, stages, and jobs. So for each commit, GitLab launches a pipeline. A pipeline is like a full iteration of your build process for a particular code change. And pipeline consists of stages. Stages run sequentially, one after another. And inside each stage, you define jobs that run in parallel, one to another. Now, artifacts can be passed only between jobs of different stages. You cannot depend, for example, in job T, you cannot depend on artifacts from job S, but you can depend on artifacts from job X and Y. And in job Z, you can depend on artifacts from every job that was executed previously. Now, where does caches fit here? Basically, caches can be passed in every direction here except to the past because you cannot reverse time. So it depends on the cache keys you define. And you can pass it vertically between pipelines and so on. You can probably even pass it across projects, but that would be pretty questionable decision. And with that comes first common pitfall. So this talk is going to be about recipes and common pitfalls that people do when using those tools. So first common pitfall with artifacts is not specifying dependencies key in the jobs. For the first stage, this does not matter because you have no jobs in previous stages. Basically, this is the first stage. But if you define a job in the second stage and you don't specify dependencies, this means that GitLab will have to download artifacts from all jobs of the first stage, even if you don't really need them. So artifacts is a distributed concept, which means artifacts are uploaded to S3. And GitLab documentation says that by default, artifacts from all previous jobs of all previous stages are passed to each job. And if you want to avoid that, you have to specify empty array in the dependencies key of your job. And if you want to specify dependencies, then you just point out jobs you depend on in this key. Now let's talk about cache options that are available at Grammarly. There are 3 of them. 2 of them work in GitLab CI YAML. You specify cache : key, and then you write which paths you want to cache. These are distributed and local. But the thing is that they have exactly the same syntax, but the choice is made when you set up runners. So you, as an author of GitLab CI YAML, cannot choose between distributed and local cache. The choice is made by platform team, and platform team chose distributed cache, which is actually quite good, because we have a third option which sort of emulates local cache. And it is basically the same as local cache for all purposes. And the third option is persistent volume. Now, persistent volume can be used together with distributed cache in the same job. And the way you use it is you just write files to /cache folder, and they will be persisted in the same GitLab runner instance. So if next build falls on the same GitLab runner instance, it will get the freshest cache possible. If a build after the next one falls on the same GitLab runner instance, it will have slightly stale cache, which might still be useful or might not be useful, depending on the contents of cache. So when I'm talking about GitLab, I'm not telling you what you put in the cache, right? Because it depends on the tools you use. Basically, when I'll talk about Gradle, I will mention what you can put in the cache. But the trick is, if you use distributed cache, basically every runner will have the freshest cache. But if you use local cache or persistent volume, you might get slightly stale cache, depending on the number of runners you have. If you would have just one runner defined for your project, then you would still always have a fresh cache. Now let's talk about how distributed cache works. Well, it's very simple, and I actually think that this is too simple. Because what it does, it essentially downloads and extracts a zip file from S3, then it runs your job, and then it packs and uploads a new version of that zip file. Now, do you see what's missing here? As a developer, like if you would define a very large cache, which would take 500 megabytes, is there something missing here? So the first thing that's missing is no checksums, no hash sums. Basically, nothing is compared. It's non-incremental. And the second thing is this is not an rsync. It's literally downloaded and uploaded every time, the whole zip file. And the third thing, there is no cleanup, automatic cleanup mechanism. So whenever you want to clean that distributed cache, you have to reset it via GitLab user interface or change cache key. Now, first 2 points together mean that distributed cache is always downloaded and uploaded even when there are no changes to it. And there are 2 minor annoyances, one of which is that you can only cache files that are inside your project directory. And the other is the absolute path to those files will differ across GitLab runners because your project directory is different on different GitLab runners, and it includes runner ID. I'm jumping ahead here because it's not immediately clear why this matters. But I'll tell you, this matters to some Gradle optimizations. They work based on absolute paths. And if you take files from one GitLab runner and then pass them to another GitLab runner, and the absolute path on that GitLab runner is different, the optimization will just not see those files. It will not find them, and it will not work. But there is a workaround, and the workaround is to set git clone path variable in your GitLab CI YAML to a value that is runner independent, that does not include runner ID. Next, let's talk about how do you choose a key for a distributed cache. And I present 3 options. In fact, there is like limitless number of options, but these are kind of common, or you will often see them. And you can cache per repository if you define key as CI project name. This means that you use one cache for all branches in your repository. And the possible problem here is that it quickly becomes a union of all branches. For example, if you add some dependencies in one branch, and then you revert to building master branch will get those dependencies even if the branch was not merged into master, and that must be somehow handled outside of GitLab. So, for example, Gradle has automatic cleanup of caches, but yeah, you depend on some other tool which is not GitLab. GitLab has no mechanisms of cleanup. And second option is to cache per branch, which means that every time you create a new branch, first commit will take a while, will take more to build, basically, because you will have no cache for this branch. And third option is kind of ridiculous. It's cache per pipeline. Pretty much no one uses it because you can use artifacts instead of it, and you should use artifacts instead of it. This is when you want to pass some intermediate build results between jobs of a single pipeline. Use artifacts instead of third option. Now, you can also add job name to those keys and have separate caches for different jobs you have. But that is optional, and it depends on which tools you use inside GitLab. Now, there is a trade-off in distributed cache that I have already presented to you, which is network time versus build time. By using distributed cache, you essentially cut down the time it takes for example, for Gradle to build your project. But you add time to download this cache from S3 and to upload it back to S3, right? So there is a trade-off. And the bigger you make this cache, the more time it takes to download and upload it. But local or volume cache also has a trade-off, which is number of runners versus cache freshness. So the more runners you have in your project, the less probable it is that you will get the freshest cache on your next build. So let's come to comparison table. The thing with volume cache is that more runners, bigger average lag. And it depends on what you cache. Some caches are very prone to staleness. So if it's stale, it's a complete cache miss, and the cache is absolutely not useful for you. But other caches can take it quite okay and can still be beneficial if they are slightly stale. And I'll talk about this later. So which cache to use? These are some rules of thumb I came up with. So use volume cache when stale cache is still beneficial. And the size, use it when the size of files is big, so it takes a while to download or upload them. It is reasonable to use volume cache when you download files and when you not produce them with your build, and when the number of build runners is low. And low is a subjective word. Basically, when it's less than 10, you can be sure that it's okay to use volume cache, I think. And then you should use distributed cache when stale cache will mean complete cache miss for you. So when you really need the freshest cache on every build in order to get some time savings. And when the file size is small, so it doesn't take a while to download, and when the files are produced by your build process. Final advices on the goals that I have presented in the beginning. Not sure what to add to this, but I have not talked about simplicity here because it is not directly related to speed and optimizations, but GitLab has a feature called templates, and you can use templates to avoid config duplication in GitLab CI YAML. But sometimes you can save even more space in your GitLab CI YAML by using one-line tricks. I will show one such trick a little bit later. Also, I did not talk about reproducibility here, and the main advice for reproducibility is if you need to install something, please do specify versions in your scripts, in your script. And if you use a lot of caching and scary cache techniques, please do clean builds in master branch. And now we come to Gradle. So Gradle has a large optimization zoo, which is 6 optimizations. And they're all different in magnitude. Oh, it's not very readable on our screen, sorry about that. But for that, I have a next slide, which makes it more readable, definitely. The same 6 optimizations. When you build locally, all of them are enabled by default. So you don't need to do anything to get those speedups when you build on your machine. But on CI, if you want to enable them, you must preserve certain files that store metadata info for these optimizations. And some of those files are pretty big. So we will decide by the end of this section on how would you store them with GitLab, whether in distributed cache or in volume cache, or maybe you don't need some of those optimizations at all because they will add very little benefit to your build process. So first of all, dependency cache. Now, dependency cache is about saving the third-party libraries you need to build your project. And Gradle puts those libraries in a certain folder, and this is the biggest of caches. Typically, this can take up to 500 megabytes for a typical project, maybe even a gigabyte. This is pretty big. And to download it from the internet on every build might be wasteful. Now, you can check whether you are downloading it by checking build log and just searching for download strings. You will see the libraries you are downloading, or maybe you will not see this, and that will mean that you're using some sort of caching here. Now, incremental build. Now we get into a little bit confusing territory, and I'll ask you to follow very well on these descriptions because there are very slight differences between next couple of optimizations, and it might be hard to follow here. So incremental build essentially can skip Gradle tasks where if the inputs for the tasks and the outputs for the tasks have not changed since last execution in your local machine, basically. So Gradle stores input files under project.dir.gradle. It stores hashes of those inputs. And then it stores output files in your build directory. Those output files, for example, for Java, can be generated class files. So they will lie in /build/classes. So if Gradle runs and it sees that your input files match to your output files exactly, it will simply skip the task, and that will output that task name : up to date in the build log. So this optimization is also called up to date checks very commonly. Local build cache. This is very similar to the previous one. However, it doesn't require that exactly previous execution was on the same input files. Essentially, it stores every execution hashes in a list, and on the next execution, it checks your inputs against that list, and if it finds the inputs you have right now in your project directory in that list, it will take the outputs of the task out of cache. So instead of using the last execution, you use any previous execution here. And this optimization needs to be enabled via argument -- build cache. It is disabled by default in Gradle. And tasks that are cache hits will be marked from cache in the build log. Remote build cache. This is, again, very similar to the previous one. However, the files used to carry this optimization over are not stored on the machine that runs builds, but instead they're stored on remote Gradle cache server. And Artifactory can serve this cache. Besides enabling this cache in command line when you call Gradle, you also need to specify the URL of the remote Gradle server, or remote Gradle cache server in your settings Gradle. Otherwise, you cannot use this optimization. Now, incremental compilation. We already had incremental build, so this might be really confusing. So incremental build is a language agnostic feature. It does not know which language you're using. It just checks input files versus output files, and that's it. But incremental compilation is actually a language specific feature. So it exists only for some languages and prominently for Java. And what it does, it allows you to avoid full recompilation of all your Java classes if just a few classes changed. If just a few classes changed, it might be enough to rebuild just those classes and the classes that depend on them and save you some time. And the last optimization is compilation avoidance. This is also language specific. It's very similar to incremental compilation, but what it does is if class B changed and class A depends on it, it will avoid recompilation of A if B changed in interface compatible way. If only internals of B changed, then it will avoid recompiling A to support that. And now we come to a confusing comparison table. Now, this might be a little bit hard to consume, but I tried to highlight, first of all, the sizes of files produced by those optimizations and the time savings. And also the last thing is it beneficial? Is this cache still beneficial if it's stale? So if we are getting not the last cache, but a cache from a build before last, for example, or a build that happened like 3 commits ago, is it still useful? So, for example, for dependency cache, you might notice that dependency cache is still very useful, even if you get dependency cache from 10 commits ago, because dependencies change so rarely. You rarely add libraries to your projects. And even if you do, usually you have some baseline, which is pretty big, like 20 libraries, and then you add 2. And if a build gets a cache that had 20 libraries, it is still very useful. It saves you a lot of time on that subsequent build. Now, some of these optimizations are complete hit or miss. For example, incremental build is a hit or miss. If you're getting a stale incremental build files from like commit before last one, they are not really useful at all because any small change will completely invalidate this cache. And now we're coming to official advices here. Now Gradle advises you to use remote build cache, and also it is a little bit less loud, but they also advise dependency cache. At least they are not actively against using it on CI. However, I have spent a lot of time trying to enable all of these caches on CI for my project, and I actually succeeded in it. But then I realized that some of them are really not that useful or not that beneficial. So I turned them off to simplify my project a little bit. And this is my recommendation. Basically, you don't really need remote build cache, even though it's recommended by Gradle. The reason you don't need it is because you rarely run your builds on exactly same files that you had before. Like, when would you need it? When you change it, README file maybe, right? And there are not many other cache hit situations here. Maybe there would be more cache hit situations for remote and local build cache if you would define your own exotic Gradle tasks with some small and rarely changed set of inputs. But for typical Java project, the cache hits will be too rare here. Now, when we come to incremental compilation and compilation avoidance, it is useful to use those features if compilation takes a while for your project. But this is also pretty rare. So most projects would compile in like less than 10 seconds, unless they're really huge. Maybe auth server would take more. I have not tested it on auth server. Maybe that would make sense there. So if your project takes a while to compile, then I would advise using distributed GitLab cache to store incremental compilation information and use it across your runners. Some GitLab recipes for Gradle. Now, if you want to enable dependency cache, I recommend doing it via GitLab volume. And all you need to do is just to define Gradle user home and put it under /cache folder. That's all you need in Grammarly setup. Now, if you decide to enable more cryptic optimizations, you would need to define git clone path as well to make GitLab check out your project in a constant folder across all GitLab instances. And also you would need to define cache key and cache some files that are produced by those optimizations. And last GitLab recipe is about running clean build in master. And this is only relevant if you decide to use those incremental compilations. And the reason you would do this is mostly because those features like incremental compilation and compilation avoidance historically were a little bit buggy, and Gradle admits it. So sometimes they would include classes that you have already deleted in your jar, and you probably don't want that in master branch. Also, yeah, I think it's just a good practice to run clean builds in master, so you're sure that all your tests pass and you have a very reproducible result. And with that in mind, let's go to Docker. Now, here are the optimizations available in Docker. Layer cache and that's it. Basically nothing else, at least nothing else that I know of. As I said, I'm not a huge expert on those tools. That's all I learned during a couple of months at Grammarly. And is it used in your GitLab builds? Now, what do you think is the answer? The answer is no, unless you do something special to actually enable it. By default, it's not used because you're building Docker inside Docker, which means you're building in a disposable environment. Nothing is passed. How would it be used? No, it's not used. But you shouldn't actually need it. That's the interesting part here that you probably did not expect. And the reason you shouldn't need it is I will show you that you can write your Docker file with GitLab. You can write your Docker file so simple that there will be nothing to optimize at all. Like there will be nothing to cache in that Docker file. So how layer cache works in a few words. Basically, it takes command arguments, the Docker file command arguments. It remembers it as a cache key, and it also remembers the effect that command had on the resulting image. And the effect is just a sum of all file changes it made. And the sum of those file changes is called Docker layer. And the sum of all layers is called Docker image that you get in the end. Now, the interesting thing is that if one command was changed and it results in a cache miss, then all commands below it will also automatically miss cache. And that's called cache invalidation. And that's an interesting thing because you really need to take that into account when writing Dockerfile. You need to think about which lines will often result in cache misses and put them, usually you put them as low as possible. So cache misses happen after all cache hits. Then you get the fastest Docker build you can get. And now let's come back to what I said in the first slide, that you probably won't need layer cache. You won't need layer cache because complex Docker files are the things of past in GitLab, hopefully. Hopefully in GitLab, you can achieve a Docker file as short as this. This is like full Docker file, 5 lines. What it does, it simply takes the distributive of your Java application, it copies it inside the container and runs it. It does nothing else. And there is absolutely nothing to cache here because this tar archive, it changes on every commit. You cannot cache it. And there are no installation statements. There is nothing here. And there is no multi-stage build here. But not every Docker file is as short as this. And even in our services, even after I tried hard to optimize them, we have, for example, docprots where we have where we need to install Node.js and all of its dependencies, and we need to do it in Dockerfile as well. So a simple but insightful flowchart on how to decide whether you need to enable layer cache or not. Now, how to enable layer cache? I'm not sure you all can read it, but you probably don't need to do it now. If you're interested, you can get all those slides and just copy the result. But the idea is that you pull the latest image before you do Docker build, and then you push the result of your Docker build into the latest image. And by doing this, you add cache from statement in your Docker build, and you say cache from latest. Now, this might look a little bit wasteful to you because this does not store this image you're pulling locally, right? It gets it from the internet every time. But if you think about this, if we go back, can we go back? This line from, it downloads a pretty large image already from the internet. Like the first line, which gets the base image, it already downloads quite a lot from the internet. If you download the whole image, it usually doesn't add too much to it, but it includes the base image. So it already includes that first line that you would anyway download. So you are not really doing too much waste by pulling this before build. And now let's talk about the order of commands. So I've mentioned that you can inadvertently invalidate the cache too often, and then you will get no benefits of layer cache. So this is a real example from our project docprots. I've recently made change from the top version to bottom version, and it saved about 1 minute of Docker build for that project. And the trick here is that you have a slow command, which was kind of last in the sequence of commands, which means it was never taken from cache, even when I enabled cache. Well, cache was disabled in the first place, but even after I enabled it, it was not being cached because it was too low in the Docker file. And there were other commands above it that were invalidating this cache on every commit, essentially. So after moving things around, I get the same result, but now the slow command is cached. And since it rarely changes, it's pretty much always a cache hit. Questions? This is almost the last slide, guys. Come on.
Thanks for the great talk and for all the work you have done. And I would like just not to ask a question, but to add up that Docker 1809, if you build with BuildKit, you can actually cache something in volumes. It has like some new syntax features, so you probably could like check this out, but it won't really change anything in this presentation. So yeah, thanks for the good work.
Okay, thanks. Thanks. Yeah, I have not really used BuildKit, and to be honest, probably out of those three tools, Docker is the one least investigated by me. So I'm least experienced with Docker compared to GitLab and Gradle as of today. So thank you for inputs. Anything else?
Thank you. I also don't have questions. I would like just to say thank you for the research, because with your research, we could apply some optimization into acquisition pipelines, for example, which will increase, speed up the builds with Gradle caches. So
yeah, thank you very much. I found that moving dependency cache from distributed GitLab cache to local or volume cache actually gave me a pretty good speed up even in SSO project. I just tried it today, and it really seems faster, considering that we have just 3 or 4 runners, I believe. It means that it is pretty much always available, even though it's local, but there is absolutely no network time associated with downloading or uploading it, which is cool. Okay, that's it. So I want to say thank you to you guys now. Thank you for all the support you gave me with GitLab and with experiments. I had to run a couple of my ideas and to try them, and Dima and Marina had to spend their time to set up some custom things for me. And thank you, Sasha, for giving me motivation for this talk. Okay, San Francisco, no questions? Okay, hope you heard it all. Wave if you heard it. Thank you.